In last recording, I talked about Coulomb's law, talked about how to calculate the magnitude of the force, and discussed the direction of the force, and of course, all forces have those properties of magnitude and direction. That's what it means to be a vector, of course. And so I said, okay, let's do a couple of examples, and so this will be the first one. A thing that I want you to notice in this example and in the subsequent examples is that although the electric force is a new force for us, and it's a little more complicated to calculate than other forces that we've seen up to now. The fact is, however, it's still a force. We still, as I just said, need to calculate the magnitude and a direction. It's still a force in the sense that it obeys Newton's second law, which means that it causes an acceleration just like every other force does. So although there are some new ideas associated with the electric force, the ideas that you're already sort of comfortable with, the idea of a force causing an acceleration, and so on, are still just as applicable to the electric force as they are to the gravitational force or the tension force or friction or anything else. The other thing I want you to take note of, which is a consequence of what I said also a moment ago, which is that the actual calculation of the electric force is a bit more complicated than other forces you've seen. To be specific, the electric force, and I mentioned this in a previous lecture, the electric force is dependent on distance. How big a force that a test charge experiences due to the presence of a source charge is going to depend, among other things, on how far apart the source charge and the test charge are from each other. And in fact, by the way, maybe you've noticed, I've snuck in some new vocabulary, some new language, and in the course of this example, I will define that language a little more carefully. All right, so I also previously started out, and then I changed my mind, to calculate the force between the electron and the proton in a hydrogen atom. So I dodged it before, but let's come back to it. So the first example. Calculate the force on the electron in a hydrogen atom due to the proton, which is the nucleus, due to the proton, the nucleus, in other words. All right. So step one for solving any physics problem, the very first thing you have to do always is draw a diagram. So we'll do that. If you have to draw a diagram. Reason is, if you can't see it, you can't solve it. So we have a hydrogen atom. That consists of a proton with an electron orbiting it. Remember that the electron's mass is 1,835 times smaller than the mass of the proton. It's for that reason that we think of the electron as orbiting the proton rather than the reverse. All right, so we have a proton, positively charged. We have an electron that is out here somewhere. It's orbiting. Now, this is an issue we will come back to, but I want to mention it. I'm going to try to mention it almost every time it comes up. And that is that when we talk about the electron orbiting, the usual picture that you see is that the electron is drawn as if it's orbiting in a circle, but that's inaccurate at the very least, and downright misleading, even worse. And that's because this phenomenon is actually a three-dimensional phenomenon. That is to say, the electron doesn't just orbit in the plane of the whiteboard here, but it orbits everywhere at a fixed radial distance. And so it's the orbit of the electron is better thought of as an imaginary spherical shell that extends up here in front of the board and behind the board, as well as around in the plane of the board and so on. Unfortunately, I'm not really able to draw that, so we'll just leave it at that. Right. So then that's that. The two charged particles are separated from each other by this distance r. And let's see, I think I want another color here. We like lots of colors. All right, I'll use this. Hopefully you can see this on the recording. The actually, I think I hate that color. Oh, I'll just use black, I guess. Okay, the electron is going to experience a force on it from the proton. This is an electric force, of course. By the way, from this for the time being, from this point forward, unless I explicitly say otherwise, anytime I talk about a force for the next several lectures, you can assume that I'm talking about talking about an electric force. Right. So if I say force without any qualification, you can safely assume it's electric. Right. Okay. We're going to draw the force vector on the electron, because that's what we're asked for, the force on the electron. So we're going to draw the force vector on the electron, and we'll have to figure out what direction it points. And we will follow the rule that I mentioned in one of the previous lectures, and that is that if two particles have opposite sign of charges, they attract each other. If they have the same sign of charge, then they repel each other. In this case, obviously opposite charges, and so the force vector on the electron is going to point directly toward proton. Okay, good. And let's see now. So that's all right. So that's our diagram, I guess. That's pretty much all there is to that. Step 2, solving any physics problem. Impose a coordinate system. Okay. As it has always been the case, you are free to define your coordinate system to be anywhere you want, put your origin anywhere you want, orient your x and y axes anywhere you want, and we will make free with that choice. I guess I'm going to go ahead and, again, I don't have to do this, but this is convenient. I'm going to put the origin of our coordinate system at the location of the proton, first of all. And second of all, because I don't want to have to deal with angles unnecessarily, I'm going to define my x-axis so that it runs along r. Now, it's true that at the, I think it was at the end of the last recording, when I mentioned Coulomb's law, which I hope you've already figured out by now, that's the mathematical approach we're going to take, that I attacked on the unit vector r hat. I'm going to, and I could use r hat, probably should use r hat here, but I'm going to avoid that for now, just because I'm trying to get you more familiar, more comfortable with the ideas, and I don't want to dump too many new things all in one go. So we'll just stick with Cartesian coordinates. So I will define my x-axis to point like this, my y-axis, as I say, there, so that the origin of my coordinate system is located at the position of the proton. And so with this choice of coordinate systems, now you see our force vector is pointing in the negative x direction for our chosen coordinate system. Kind of a peculiar angle, but there's no harm in it. I mean, remember, the electron, we've caught it at one single instant in time. The electron is actually orbiting all over the place in a fixed radial distance from the proton. So, yeah, so it's pretty much no harm choosing my coordinate system like this. Okay, so that's that. And then finally, step 3, solve the problem. All right, so we take a look at this, and the question asks us to calculate the electric force on the electron. So what do we have? We have a couple of particles, things that we know. We know their masses. We know their charges. We don't necessarily know their distance, although actually we do, and I'll explain that in a moment. But we know their masses, and what I'm doing is I'm thinking my way through the problem. How am I going to tackle this? So a lot of times I think, okay, well, I've got mass. I'm asked for force. F equals ma, Newton's second law. That sounds promising, but the problem with that, I want the force, I know the mass, but I don't know the thing's acceleration. So that looks like kind of a blind alley. Maybe that's what we'll end up having to do, but let's keep thinking and maybe something else will occur to us. What else do I know? I know their charges, and I know the distance between them. Coulomb's law involves the charges of the two particles and involves the distance between them, and that gives you a force. Okay, Coulomb's law sounds like the thing to do if I can figure out the distance between the two particles. So we'll use Coulomb's law. So the first thing I'll do is I'll simply write Coulomb's law down in this particular example. Well, you know what I think I'll do first is I think I'll write down the general form of Coulomb's law first. So Q1, Q2 over R squared. And then I'll even put R hat just because. Okay, so this is just Coulomb's law in general. The electric force depends on, is proportional to, this is the proportionality constant. I haven't actually told you this numeric value yet. I will in this problem. Q1, Q2, one of these is your source charge, the other one is your test charge. Again, I haven't formally defined that notation yet, but these are the two charges that are interacting in any case. R is the distance between the two charges, and R hat is the direction that our force vector is going to point. Okay, R hat. So what I want to do is take this general formula and replace the symbols in it with the specific symbols in our specific problem. So I think I'll move over here. Okay, so our force here is going to be K. Okay, one of these charges is the source of the electric force. The other one is the one experiencing the electric force. The way the problem is asked. I'm sorry, I need to do something here. The way the problem is phrased, we want the force on the electron due to the proton. So the proton is the source of the field. It's our source charge. The electron is the thing experiencing or testing the force, and so that's our test charge. So we have the proton has a charge, and remember I labeled that Q sub E, elementary charge, and the electron also has that same charge. And then the distance between them I called R there as well. And then as far as our direction is concerned,
You are currently the only person in this conference.
All right, sorry about that. I had technical difficulties. I pulled my microphone out of my computer here, and so that interrupted things. Okay, so I think I'm back. Yeah. So as far as what I was starting to say was, as far as the direction of our force is concerned, I mentioned that a moment ago, and that is that the force is pointing in what we define to be the negative x direction. So in substituting our specific variables into the general form of Coulomb's law, I end up writing negative x hat direction, or negative k q sub e squared over r squared r hat. At this point, you might be wondering what about the fact that the electron and the proton have opposite signs? And so you might be wondering about that. And then if it occurred to you, you probably thought, oh well, he'll deal with it later. And yes, you're right about that. I will. Okay, so really, I'm sorry. This should be x hat here. Sorry, so this should be x hat, indicating the x direction, and then the negative sign here, negative x direction. Okay, so we're ready to go. First off, well, first of all, let's look up the values for q sub e and r. Well, we know q sub e. We've talked about that before. So both the proton and the electron carry the elementary charge, the quantum of charge, which has the value 1.602 times 10 to the minus 19th coulombs. And the distance between the two charged particles is actually a known value, and it's something you could look up in your textbook. And assuming I'm remembering it correctly, I happen to have that memorized, 5.29 times 10 to the negative 11 meters. Very, 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 very small distance. Okay? Atoms are really small. Okay, so there's that. And as far as k is concerned, so remember, k is just a proportionality constant. Its value has been determined experimentally. The details are not important to us right now. I'm simply going to hand you the numeric value of the thing along with its units, and I'm just going to say, trust me, that's what it is. Okay. So this is a new thing that I haven't told you before, and I'll just put it in here. K is 8.99 times 10 to the 9th, and I need to make sure I get the units correct here. And I'm going to go ahead and do my thinking out loud, so you know how I'm working on this. Basically, the idea is I'm calculating a force. The force has units of newtons, so that means the collection of everything on the right-hand side must also have units of newtons. Okay. Well, in the numerator here, we have coulombs squared. In the denominator, we have meters squared. And we need everything to cancel except newtons. And so that means that k has to have units of newtons times meters squared, to cancel out the meters squared in the denominator, divided by coulombs squared. Okay? And so we have Newton meters squared over coulomb squared. And that is, there's various names for this constant, depending on what you like. This is known as the electrostatic constant most of the time. I will tell you, at the risk of overwhelming you, that there's more to this, more meaning to this constant than simply proportionality. But that's for another day. For now, that's just the value it happens to have. So we're ready to go. And so I'll simply substitute these values in. So our force is K, 0.99 times 10 to the 9th Newton meters squared over Coulomb squared. If I have enough room for all these. All right. Times Q sub E squared, 1.602 times 10 to the minus 19th coulombs squared, divided by R squared, 5.29 times 10 to the minus 11th meters quantity squared. And you crank through those numbers. Oh, and there should be a, I'm sorry, minus x hat, the direction. And I cranked through those numbers, and I got negative 8.22 times 10 to the minus 8, if I recall correctly. Yeah, newtons. Okay, just a quick sanity check, make sure we've done things correctly. Let's see, newtons, meters squared in the numerator, meters squared in the denominator, so the meters squared cancel. Coulomb squared in the denominator here, coulombs squared in the numerator here, and but of course you still have to square the 1.602. And yeah, so the units all cancel out, leaving only newtons, which is what we need. All right, great. Now, a couple of things before we leave this. First of all, tack on the x hat here. Right. First of all, as I was just saying, don't overread this. My canceling of this 2 here. That's just the canceling it out because of the meter squared. You still have to square 5.29 times 10 to the minus 11th. Again, same here. You still have to square the 1.602 times 10 to the minus 19th. So make sure you check my work and make sure you get the same number that I did. The other thing that I want you to note, first of all, very common and completely unnecessary errors, and that is forgetting to square either the numerator or squaring the denominator, or both. It's a very common mistake that students often make, just missing that square, especially under the pressure of a test. You just sort of miss it, and you lose 3 points or 5 points or something, just for no good reason. So watch out for that. The other thing, and a much bigger issue, is perhaps you're wondering, and I hinted at it earlier, what about the negative sign? The reason I'm squaring this is because both the proton and the electron carry the same elementary charge, except they are of opposite signs. So shouldn't I have put a negative sign in here for one of these? I clearly didn't. Why didn't I? And the answer is no, I should not put the negative sign in, and here's why not. The negative sign, or for that matter, the positive sign on the electron, as well as the positive sign on the proton, as well as the negative sign on the electron, remember, those are labels, and their purpose is to remind you that the direction of the force, of the electric force that each of those types of charge cause, those directions are opposite to each other. But the problem is that if you remember when you're thinking about vectors back at the beginning of your mechanics course, that if you have a vector of, I don't know, 3 meters in that direction, if I said x is equal to positive 3 meters that way, If I then said, well, how about a vector of negative x, or so negative 3 meters? The answer is putting that negative sign on that reverses the direction of the vector. It reverses the direction the vector points. Okay, so here's the problem. If you include the negative sign when you substitute in for a negative charge, then that negative sign gets into the mathematics and will reverse the direction that the force vector points. And we'll have the same problem later when we do other things that are related to the electric force. So if you're not careful, it's really easy to include the negative sign where you shouldn't, and you'll end up flipping the direction of your force vector when you shouldn't. But we don't need to include the negative sign when we're substituting in values for negatively charged particles. And here's the reason. We already worked out the direction that the force points. We did it at practically the very first step where we said, oh, when I draw my force vector in my diagram, I'm going to have it point towards the proton because why? Charges that have opposite signs attract each other. So I've already worked out the direction of the force. I don't need to do it again when I substitute numbers. And in fact, if you do include the negative sign, as I just said, if you do include the negative sign when you substitute numbers, you're very likely to reverse the direction that this vector points. So here's the thing. When you're substituting in for calculating the force, and later on when we calculate the electric field, never include the negative sign on negative charges when you actually substitute numbers into Coulomb's law. Okay? You work out the direction based on the rule. Like charges attract, like charges repel, opposite charges attract. Work out the direction from that rule, and then from that point forward, just don't include any negative signs. Just use magnitudes, when you're substituting into your formulas. Okay, so there's that. So the next thing I think we'll do is a slightly more, not more complicated, I guess it is, a slightly more complicated example for the next one.